This is Liam Brill doing my 8.1p pass task with Miss Marple. So the first part we have is to find the maximum number of short paths for a hotel so that she can use to get from the train station to that hotel. To do that, we have pseudocode. So the first thing we do is you take a graph of the map, and for every single node in the graph, we set the distance of that to infinity. This means it hasn't been explored yet. And we set the path count to 0 as we haven't fed out the path to any node yet. From here we create an empty list which kind of acts as a queue, which we'll use for the breadth first search to search through every node. We'll add the start node to it, and the distance will be 0 because obviously it's where we're starting at, and the path count to 1 because we need to get there because it's the station. And pretty much while the list isn't empty, we remove the current node from the list and we find every single neighbor, and then we check to see if it hasn't been visited. And if this, then we set the distance of the neighbor to equal the distance of the current node plus 1. That's just because every single unit of distance is 1. So let's say we have station and then node A and then node B. And to get to node B, you have to go through station to A to B. Each one of those steps would equal 1. So the distance of node B would equal to node A plus 1. So it'd be equal to like 2. And we'd update the path count for the neighbor to equal the path count of the current node, as we know that's the like to get to that node we would take the current paths of the previous node, as that'd be the same, and then we would add the neighbors to the list. And this is just a possibility if we come across a neighbor again which has already been visited, and this current path that we're checking out has the same distance to that neighbor as previously found. All we would do is we would just update the path count of that neighbor to include the new path count, and its previous one, and then we'll return the path count. And then Miss Marple could use this to figure out which hotel has the most minimum paths. For part B, this works on connected graphs, and how to pretty much detect a connected graph. So for here, we make a new list called visited, and we basically going to try and check to make sure every single node is connected or not. We would start from any node, so just pick a starting node, and we would apply depth first search to it. The way this works is we would add started to the visit, obviously, because we're starting there, and then for every node in the graph, we would check if it's not visited, and we'd apply depth first search to that to find new neighbors, and we'd apply recursively depth first search to that to find neighbors. And eventually, after this is exhausted, we would then check to see if every node is in visited or not. If all the nodes are in visited, it means it is a connected graph, and if it isn't, well, it means it's not connected. For part C, there's a question where it says, given a graph, what is the runtime complexity? Oh yeah, so basically it's just if we're using a matrix instead of a list, why depth first search wouldn't be good. This is basically because with depth first search for a matrix, you would have to check every single one of its neighbors out. So let's say for one, we have to check here, 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 here. Here's every single column of that row for every single row. So it'd be n2 would give a time complexity of n2 because you have to check every single row and column. Compared to if it was just a list, it would just have the neighbors which it's connected to. And then for part D, we're using the simple single source shortest path Dijkstra's algorithm. So the first part, we would make the network originally, so we have like 1 and 2 would have a weight of 3, and so on. 2 and 4 would have a weight of 5. You can see that here, 2 and 4 weight of 5. Basically, all we do is we create a kind of like a queue. We would add 1, it's a starting node, would have a weight from 0 because we're already starting there. And then we would find its 2 other nodes, or the other nodes that it's connected to. So we can see here it's connected to node 2 and node 6. We would go 0 plus the distance or the weight it takes to get to those nodes, and we would update the queue. And then we'd take the next node that has the smallest weight, and then we would find all its neighbors. So like let's say 2 would have 7, 5, 8, 4, and so on. And we would update those nodes. We would have to take the previous weight that it takes to get to node 2. So to get to node 2, you take it from node 1. So that would be a weight of 3. So you'd go 3 plus the weight it takes to go from node 2 to the next node. So to get to node 5, we would take 3 plus 11, and then we would update that in the queue. And basically we probably just repeat this by removing the smallest node and then finding which nodes to that it's connected to, and then adding those to the queue. And we keep on doing this and updating it until we get down to the bottom. So yeah, as you can see here, like example for node 5, we know it has a weight of 15 to get to there. And we get to node 10. So we would go do 14 plus 3 to get to 17. I think it's up here. 5 plus 3 gets 10. And finally we get to node 9. As you can see, there is no actual way to get to node 9. There's no route that points to it. So that's kind of disconnected from the graph. And then basically with that, we could then make the new shortest tree. We'll just take all the, like in the row, which numbers were removed. So 1 and then 2 and 8 and 4 and so on. And then we would make a new graph and it shows the shortest way to get to each node. Final part, we just have a question where it is let P be the shortest path from vertex S to T in a graph. If the weight of each edge in the graph is increased by 1, P will still be the shortest path for S to T. This is false. You could have a graph, a path from S to T, which has, let's say, 4 edges in it, 1, 2, 3, 4, with length of 20. So if you increase every edge, this total length of this path would increase by 4, and its total length would be 24. Let's get a different route that had only 2 edges in it, but its previous length was a length of 21, so you wouldn't use this over this previous best path. But after the new edge increase, we would only have its total increase by 2, leaving it with a new length of 23, which would make it the new shortest path. So that's how it proves that that is or false, or that's the answer. Oh, it's a bit weird, but yeah, thanks.